All right, guys, we're back with section 2 or part 2 of our unit or section on inverse trig function integration. We're going to talk about completing the square. So sometimes when you have a quadratic function involved in the integrand, it can be helpful to complete the square on it so you can um, continue integrating. So if we have the quadratic, the general form x squared plus bx plus c, we can rewrite it as a difference of two squares. And that's important and helpful because in some of the trig, inverse trig integration formulas, you have a difference of squares. So we can do that by adding and subtracting b over 2 squared like this. So if you have x squared plus bx plus c, you can take half of the linear term, so b over 2, and square it. So half of the coefficient of the linear term and square it, and then add and subtract it. X squared plus bx plus b over 2 squared minus b over 2 squared plus c. Now, the reason we're doing this is because whenever you add and subtract the b over 2 squared, those are just constants and you're adding and subtracting the same ones, so you're essentially adding 0. But what you have here is the first three terms work out to be a perfect square trinomial, and it ends up factoring into x plus b over 2 squared minus this part that's left, b over 2 squared plus c. And then this is now a difference of squares right there. Okay, so that's kind of theoretical without any numbers or anything. So let's actually look at an example. Let me make this a little bit bigger here. So if we want to find the integral of dx over x squared minus 4x plus 7, first thing we're going to do is take the denominator and complete the square on it. So if you have minus 4x, you take the sign of the number with it. So negative 4 over 2 squared, which would be negative 2 squared, which is 4. So you add and subtract 4, and then you have the plus 7 on the end there. So this right here is going to be a perfect square trinomial. And basically whatever you squared to complete the square is what you add or subtract in the factored form. In other words, it's going to be x minus 2 squared. And then the last piece here, the minus 4 plus 7, gives us plus 3. Okay? So I can think of this as u squared plus a squared. So this would become the integral of dx over x minus 2 squared plus 3, which has the form of arctan, where u, let me write it over here, u equals x minus 2, and a is going to be square root of 3. All right, the du is just going to equal dx, so we don't have to really perform the u substitution. Everything's going to work out. So the antiderivative for inverse tangent is 1 over a, so 1 over square root 3, arctan u over a, so x minus 2 over root 3, plus c. All right. So sometimes it happens that you have a quadratic where the leading coefficient is not 1, something like 2x squared minus 8x plus 10. In that case, what we're going to do is factor out the leading coefficient from the first two terms. So you would have 2 times x squared minus 4x plus 10, and then complete the square on the stuff that's inside the parentheses. So that minus 4, we have minus 4 over 2 squared, which gives us 4. So you'd have 2 times x squared minus 4x plus 4 minus 4. Keep that all in the parentheses, plus 10. Okay. Now, this is the trinomial that we can complete the square on. So it'd be 2 times x minus 2 squared minus 4. But all of that is still multiplied by the 2 plus 10. Okay. Now, I need to get that negative 4 out of the parentheses. And since the parentheses are being multiplied by 2, I can rewrite this as 2 times x minus 2 squared um, plus 2. All right, so the minus 4 comes out as a minus 8. You add it to the 10, and you would get plus 2. And then you could actually even factor that 2 out and get 2 times x minus 2 squared plus 1, like that. Okay, so that's how we handle a situation where the leading coefficient is not 1. So just happen to have an example here where we want to find the area of the region bounded by the graph of 1 over square root 3x minus x squared, the x-axis and the lines x equals 3 halves and 9/4. So we have this region right here. We have a picture of it here, so we can actually kind of approximate what the area would be, or at least give us a boundary for what it would be. So notice this region is only 3/4 of a unit wide, and it's not even a unit high. So our answer for the area of this square, if we approximate it, it's approximately 3/4 of a unit wide and 1 unit high. So that area would be 3/4. This isn't even that much. So I know my answer should be less than 3/4 or less than 0.75 when I get my final answer. All right. So the area, let's get going here, can be represented by the integral 3 halves to 9/4 of 1 over square root 3x minus x squared. Okay. Now we're going to complete the square in the denominator. So let's do some work on this side here to look at this. So if I have 3x minus x squared, I can rewrite that as negative x squared plus 3x. It helps to factor out the negative, but be careful, that's going to change the sign of the 3x. And then you take half of that 3, half of the negative 3, and square it and add and subtract it. So x squared minus 3x plus, so negative 3 halves squared is going to be 9/4, and then you're going to subtract 9/4 all inside that. So you would have negative x minus 3 halves squared minus 9/4. Okay. So if we distribute that negative back in and rewrite it, you would have 9/4 minus x minus 3 halves squared. So this is going to be the integral from 3 halves to 9/4 of 1 over 9/4 minus x minus 3 halves squared dx. Okay. And here in this situation, the u is x minus 3 halves. And the du would line up perfectly, just giving dx. And the a is 3 halves because 9/4 is 3 halves squared. So this is going to be arcsine of u over a. And we're going to evaluate that at 3 halves and 9/4 and subtract. So this is going to be arcsine. When you substitute 9/4 in, it's going to simplify all the way down to 1/2 minus arcsine. When you plug in 3 halves, you're just going to get 0. So arcsine of a half is pi over 6. Arcsine of 0 is 0. So you would have pi over 6, which is approximately 0.524. Remember, we estimated that our answer should be less than 3/4. All right. Well, that's it for this one, guys. Next time, we're going to talk a little bit more about all the basic integration formulas and how to know which one to use and when to use it. All right, hope that was helpful. Take care.